Hello, everyone, and welcome back to our Hypercompositional Algebra series. In today's episode, we introduce one of the most important algebraic structures in hypercompositional algebra, the polygroup. Polygroups extend the concept of groups by allowing operations to produce sets of elements while still preserving an elegant algebraic structure. They play a central role in hyperstructure theory and have many connections with group theory, geometry, and other branches of mathematics. Let's get started. By the end of this video, you will know the formal definition of a polygroup, the key properties that characterize a polygroup, how to verify whether a given hyperstructure is a polygroup, how polygroups can be constructed from groups, and the definition of subpolygroup. We now introduce the formal definition of a polygroup. First of all, a polygroup is a hypergroup equipped with two additional features, the identity and the inverse for every element, and it satisfies this condition. So if we look here, E, we have an identity with X times E times X equal to X, and we have the reversibility property. And we have, of course, the associativity because it is a hypergroup. Notice that every polygroup is a hypergroup, but not every hypergroup is necessarily a polygroup. And shortly, we will give a counterexample on this. Take your time to read the formal definition presented on this slide and pay particular attention to the role of the identity element and the inverses. So we're saying here that every polygroup is a hypergroup. And hypergroup, we have only the associativity and the reproduction axiom. And the reproduction axiom here, we can easily show it from the identity. Now, what do you think about the converse? Do you still remember the bisect hypergroup? What do you think? Is it a polygroup? So let's construct it. AB. Here we have AB, here we have A, here we have AB, here we have AB, and here we have, oops. So what do you think about the identity here? What do you mean by an identity? So if we look at A times A is equal to A, and A times B is equal to A. So if you look at A here, it serves as identity. What do you think about B? Also, we have BB equal B, and B times A is equal A. So if you look here, A belongs to be A intersection AB. So in this case, A is an identity. And also the same here, B. B, it belongs to AB intersection BA. So B as well is an identity. But if we go back to the definition here of the polygroup, the identity should be scalar. E times X is equal X times Z, which is not the case here. A times B is equal AB and not only B. So not every polygroup is a hypergroup. So now what do we have? We have the group is the smallest, then we have the polygroup, and then we have the hypergroup. Every group is a polygroup, and every polygroup is a hypergroup. The best way to understand a new mathematical structure is through examples. Let's examine the examples that we have in these slides. First, we need to determine whether this one is a hypergroupoid. Now, if you look at each column here, let's highlight the columns. In each column, the elements that we have are elements of the set P. And in each row as well, the elements are in the set P. So it is a hypergroupoid. Now let's examine the reproduction axiom. Each row contains the set P, and each column contains as well the set P. So the reproduction axiom is satisfied. You can pause the video and refresh your minds about the associativity and try to prove the associativity for this one. But for now, we will try to find the inverse of each element and the identity. Now, let's look at M0. M0, this row is repeated here, and this column is also repeated here. The intersection between them is M0, and in this way, M0 is the identity element of this polygroup. Now, what about the inverse? The inverse, M0 times M0 is equal to M0. So basically, the inverse of M0 is M0. What about the inverse of M1? We need to search for row and column of M1, row or column of M1 that contains M0. M0 is contained here. So M1 times M1 is equal to M0. So basically, the inverse of M1 is M1. Similarly for M2, the inverse of M2, it is M2 as well. Are we done? Of course not. What do we need to check also? The reversibility. So we need to check for each three elements. Let's find these. X belongs to Y times Z. We have this one. You can pause the video and try this as well. Here we have another example, but if you look here at this example, we have the table is symmetric. So this one, we call it commutative polygroup. And in literature, we call it canonical hypergroup. But if you look at this example, that I will keep it for you to pause the video and try to find the identity and the inverse of each element, you will find that this one is not symmetric. Simply n2 times n1 is not the same as n1 times n2. So it's a non-commutative polygroup, and in literature, we have it as quasi-canonical hypergroup. Here we have a nice construction, starting with the group and subgroup. We can introduce a polygroup. Now, if we recall the first episode, we said that Marty's motivation for introducing hypergroup is that if we take any subgroup of a group and we put a certain hyper operation, we will get a hypergroup rather than a group. So here we are starting with, instead of working with the coset, we are working with the double coset. So we are starting with G. H is any subgroup of G, and we are taking this set that is here. Under these operations, under star, with this operation, and the inverse in this way, we are getting it as a polygroup. Now, I will put for you a few notes to think about. What if we take H as a normal subgroup, what will happen? And what if we take G as an abelian group, what will happen to this hyperoperation? What will we get? The result. I mean by the result, when I say GH with star, what will you get it as? You can pause the video, think about it, and you can keep your answers in the comments or connect with me on LinkedIn. Now, here are some elementary facts about polygroups, and we will manage to prove some of them together. We can start with E inverse equal to E. So we know that E times E is equal to E, right? Because E basically is the identity. So E times anything is the anything. So what can we deduce here? Immediately we can deduce that E inverse is equal to E. Also, we need to show that E belongs to X inverse intersection X inverse dot X. Now, in order to show this one, we will go back together to the reversibility property. X belongs to YZ. So first of all, we know that X times E or E times X is equal to X, right? Let's apply the reversibility property. What does this one mean? It means that X belongs to X E intersection EX. Of course, here EX is equal to it. Let's start with this part first. So X belongs to XE. Our aim is to get X inverse. So if X belongs to XE, what can we deduce here? We can deduce that E, this one, belongs to X inverse times X. Similarly, E times X is equal to X. We'll use it, and we will get E belongs to X inverse. In this way, E will belong to the intersection between them. I will leave these two properties. You can pause the video and try to prove. Another way to construct a polygroup from a group is the one that we will present today. Starting with a classical group, we can inject a single external element. We are calling it here A. Of course, A should not be in G. And when we are inserting it, we are taking G union this one, and we are calling it PG. The hyperoperation on PG, so now we have PG with this hyperoperation. Of course, E will stay the identity, so E with the new hyperoperation with X, it stays as X. And A with X as well is X if X is not E and not A. A with A is E. So if I'm saying here that A with A is E, immediately as if we are saying A inverse is equal to A. And X with Y, if X and Y are not inverses of each other, we are getting XY, the one in the group itself, And if they are the inverses of each other, we are getting E. Not only E, we are getting E with A. Let's look at an illustration. So all of us know the group C2 under addition modulo 2. Group of integers modulo 2 under addition. And this is the table of it. This is the plus, this is 0, this is 1, this is 1, and this is 0. What we will do now is P of Z2, instead of having only 0, 1, will have also A. What will happen now? So I will insert here A. The identity here, E is equal to 0. So E 0 circ A is A, and here we have A. And A square or A circ A, what did we say about it? It's the identity. And what's our identity here? It is 0. And A with any element, if you look here, A with X is X. So A with 1 is 1, and 1 with A is also 1. Perfect. Now, still we have 1 with 0 is 1, but 1 with 1. What should I put? 1 minus 1 is 1 in G, which is Z2 here. So when I put 1 with 1, they are inverses of each other, so it will be equal to what? EA, which is 0. So we will put here 0A. And this one is a polygroup. Here we have another illustration on Z3, the group of integers modulo 3. I invite all of you to try D3, for example, to try Q8, to try D4 or S4 or A4, the alternating group, the symmetric group, the dihedral group, or the quaternion group, and try to find the associated polygroup of it. Examples like this help us transform the abstract definition into something much more concrete. Just as groups have subgroups and hypergroups have subhypergroups, polygroups do have subpolygroups. And when we say subpolygroup, of course, it shouldn't be empty, and it should be a polygroup. Now, how do we prove that it's a subpolygroup? All what we need is to prove that binary closed and the inverse does exist. So these are the only things that we want to prove. We can take an example together. So if you want, we can take this example and try to find some subpolygroups of it. So let me just do it here. Now, if you look at the identity only, it is a subpolygroup. Now, can I take 0 with 1 only as a subpolygroup? We can. Let's try 0 with A. It is a subpolygroup. You can construct for each of them its table. So here we have 2 subpolygroups that we found. Let's try something else. You can try this one as well. So N0 only is a subpolygroup. What about N0 with N1? Also, it is a subpolygroup. Now, if I insert N2, N0 with N2 as well. It is a subpolygroup, but N0 with N3, it's not a subpolygroup because N3 with N3, it gives us P prime. And the subhyperstructures are very important in understanding the structure itself. Here we have some polygroups of 3 elements. I invite you to pause the video, think about this one, whether it's a subpolygroup or not, whether it's a polygroup or not, try to find some subpolygroups of it, find the inverse of each element, the identity in each of them as well. Let's summarize today's lesson. So we learned the formal definition of a polygroup, the role of the identity and inverses, how to recognize and verify polygroups, how polygroups can be constructed from classical groups, and the concept of subpolygroup. Polygroups provide a fascinating extension of classical group theory and form one of the central topics in hypercompositional algebra. Thank you for watching this episode. And if you have questions, please leave them in the comments so that I can answer you, or you can connect with me or follow me on LinkedIn by just scanning the QR code. See you in the next episode. And from now till we meet again, have a great day or great afternoon or great evening from whatever the time that you are watching us.